Eeny, meeny, miny, mo. Catch a Feynman by the toe. Oh, that says we're live. I guess what's going on? Memes here. So, today we're going to be discussing a little bit of a mind worm, a little bit of a mimetic that just kind of like was crawling around. This was spurred today as my algorithm brought me to a nice World Science Festival. Shout out to Brian Green, and I was in an episode with Professor Juan Maldacena, who helped bring the ADS CFD correspondence, the anti-center space conformal field theory correspondence, aka the holographic principle, into more of the mainstream, or no, that's not a good word. The generalized consciousness of, oh my God, if we can tell what's going on the surface, we can tell what's going on within a given thing. Okay. Now, I remember hearing about that, like many of y'all who may be watching this video, algorithmically came up, or even, oh God forbid, you clicked on it. Oh God, I apologize. Uh, but I had heard that, and I had been going back and listening to some of Professor Feynman's lectures from like the 60s and 70s, and at one point, he got to describing something that, and again, I'm not a professionally trained physicist nor mathematician. I am a dude that pretends to kind of be a science communicator on the internet. But as he was describing in some of those lectures, I'm like, that sounds very familiar, except Professor Feynman gave that lecture in 1964. Um, Professor Mel saying his paper wasn't until 1997. And then if you just do a cursory Google search and you go to Wikipedia, you look up the holographic principle, you're going to see, I think, what is it? There was like a string theory correspondence kind of talking about holography and stuff like that in 1978. That was still not 1964. So that's what we're going to be talking about today, just because I'm like, and again, not to get conspiratorial or anything like that, but allegedly, even Professor Keating brought this up. Professor Feynman at one point or another said something about, "Oh, I have like, a couple of patents and stuff like that," and people are checking, saying, "We don't see any patents listed." Was Professor Feynman lying to us? I'm just saying that in a very publicly available lecture that you can find online, we're going to go through right now. Um, It sounds, and again, it's stated in a different way. Again, somebody please point out how horribly wrong I am. I'm sure somebody will do that. But let's get to what Professor Feynman actually said. Uh about oh God, 70? No, 60. About 61 years ago. Okay, let's go to the right tab. Okay. You can see I have a transcript up here, just in case if we would like to know what he's actually saying. So.
You can state the law in another way. It says the following. You don't have to know what's going on anywhere outside of a little ball. If you want to know what the potential is here, you tell me what it is on the surface of any ball, no matter how small. You don't have to look outside. You just tell me what is in the neighborhood and how much mass there is in the ball. The rule is this, that the potential at the center is equal to the average of the potential on the little ball surface minus this constant that's over there in the other equation, divided by twice the radius of the ball. Let's suppose the radius of the ball is called A, and then multiplied by the mass that's inside the ball, if the ball is small enough. Now you see that this law is different than the other one because it only tells what happens at one point in terms of what happens very close by.
Okay. Now, again, it's but apparently, according to my knowledge, according to the whole ADS-CFT correspondence and everything, we can go take a look at that. Um, Basically, it's that amazing thing that seems to happen. It's like within a black hole or whatever, we believe this strange thing, this ultra dense, usually thing is. If rather than having to know all the stuff that's going on in the volume, you can basically, hypothetically, theoretically, tell only from the surface area. And that seems really amazing. And and then I go back and I listen to this clip and I'm like, it sounds kind of similar. It kind of sounds kind of similar to me. I'm like, wait. But this is from character of physical law, which uh another version of this. I don't know. I don't know. We're kind of black and white. Hold on. Let's exit out. Feynman, physical law. So Feynman, the character of physical. Oh, they got a PDF too. All right. Bring this up. Share with the class. Okay. So it's some of the Feynman series of lectures, and at least according to our general thing here, is a series of 7 lectures. Okay, excuse me, the character of physical law is a series of 7 lectures by physicist Richard Feynman concerning the nature of laws of physics. Feynman delivered lectures in 1964 at Cornell University as part of his Messenger lecture series. So again, this was 61 years ago now, and I'm just a rando on the internet. But I'm just hearing this thing. It's like, all right, you can tell stuff that's going inside by knowing what's going on the surface. I'm like, just chunking that and lumping that together. I'm like, did did he know? Did he substantiate, or was this just an substantiation that was built upon that led to the holographic principle? I mean, it's not like Professor Feynman knew a whole lot more that he wasn't sharing with us or anything. I mean, that would be weird. But I digress. I'm sorry. I'm rambling. I'm rambling now. Let me get back to our friends in the chat. Welcome, Jax, as well as David. We're going back to the old school stuff. Yeah. Hey, we're going back to some of the classics, so to speak. Uh, yeah, Rick is pointing out that to see God's lab's law of gravity is also known, but I don't know. People don't seem to talk about it as much. Also known as the fundamental theorem of calculus. Uh, you can know the mass of a volume from the flux through the closed surface. I think Professor Feynman, he was saying that if you have a ball, if you're trying to tell what's going on within the center of that ball, and I think Bill Manuel and I have kind of also had some discussions about this. He's going about it from was it the EDOF, extended degrees of freedom, or something. I need to sit down and listen to that again. But he's saying that basically, if you have the surface and you have the mass, and you want to know it, I think he's mostly talking about effective forces and stuff like that. And then, as long as you were to partition, so to speak, and tell what's going on within that spherical area around it, you should be able to do calculations. Is that the ADSC if they correspond? No, probably not. Uh, but it's just interesting where it's like this revolutionary thing. Oh my God, it changed our mind. I think it's like something else says, it's like the highest cited physics paper in the world or something like that. Hey, I mean, it seems to be a fantastical thing, but I'm just knowing that that was a thing and then going back and just listening to some of these lectures, it's like, that sounds very similar. Again, it's probably just me as a crazy person on the internet just grasping out there for straws, because I mean, you need to have straws, right? America runs on noggin. I claim. Let's see. Let's see. Jonathan is praising the Almighty God. Cool. Hey, welcome, Alex. Good to see you. All right. People don't there to his shit. What? People are crying about what other people said on the internet? Why? Why would people complain about what other people have to do? Geez, you'd think they'd have like important stuff to do rather than just scream on the internet. It's then again, I mean, I spend plenty of time screaming on the internet, but then again, I'm a terrible, horrible, no good, very bad person. None of you should be here. What terrible influence. Uh, let's see, where are we? Okay, let's go back to Professor Feynman for a second. Well, let's listen to this again, just because this is, at least for me, it gets the old noggin that shocked. All right, let's go back over here. Okay, so yes, yes, how I organize my thoughts, just random timestamps and having to find my own comments on YouTube and other social media platforms. Let's go back. Let's go back. See what which law he's talking about. It's so that's 35. Let's go to 34. I think I think he's trying to get out of spooky action at a distance or something. Okay. So apparently we're talking about field laws, and I think he's talking about field theory because, well, I'm pretty sure at this time he was working on, was it QED and maybe going into QCD? Well, I mean, QFD is literally like quantum field theory. Uh, QED is quantum electrodynamics and stuff. So, I mean, that sounds like okay. Well, 64. Professor Wolfram worked some point during some of the mid to late 70s and 80s within the particle physics uh, community. He had worked with Professor Feynman in the 80s. I mean, if this is in 64, though, that's still 16 years away from the 80s. That's the thing. It's like if it was in 95 or even basically if it was after the paper, you're like, ah, no big deal. But you're like, that seems so surprising to folks. But you go back and you listen to this, it's like I realize I'm bloviating and also justifying my fair use critique. I think this has been out long enough and this has probably been clipped in part. I think they were trying to avoid copyright by putting the periods and the character of physical law there, but this video is also from, okay, yeah, it's from, oh God, this video is on its way to being an adult, 14 years old. Oh, sorry. Yeah, thank you. Ab. Uh, let's go back over here. Sorry. All right. I'm going to turn up the audio a little.
As I've described before. The regular way, I call it Newton's law. Now there's a completely different way. That law says that the force depends on something at a finite distance away. See, it has what we call non-local quality. The force on this depends on where that one is over there. Now, you may not like the idea of action at a distance, that it can know what's going on over there. So then there's another way of stating the laws, which are very strange, and it's called the field way of representing the laws. And it's so very hard to explain, but I just want to give you some rough idea of what it's like. And it says, different thing, completely different thing, that there's a number at every point in space. I know it's a number. It's not a mechanism. It's the trouble with this whole physics, that it must be mathematical this way. There's a number at every point in space. Here's a number, and so on.
Okay, so I believe that's the concept of a scalar. You can assign a magnitude to essentially any point, whatever the heck that is, within space or some realm, so to speak. Uh, that's the way I generally have understood it. Uh, well, see, Jax, that's why people were getting outraged about the standard outrage of the day. And at one point, I'm just like, just cut the floor plate. Legalize bowling, in my opinion. Because everybody knows the ultimate limit of what somebody truly believes in is what they're willing to sacrifice for. I'm just saying everybody knows that sacrifice by typing some random mean words on the internet to somebody they've ever met is obviously such great sacrifice on there. But all I know is a couple of local council representatives in Brazil got into a 5 round cage match over a water district issue. You want to know what? I don't really care who won. I believe both those gentlemen really cared about what they were saying. I believe they were true believers. So ultimately, my solution to a lot of just conflict is listen, if you're willing to get in the ring and legally basically have the opportunity to eat a knuckle sandwich for something you truly believe in, I probably believe you truly believe in it. If not, maybe you don't. Sorry, sidetrack tangent. Let's see. Okay, so Rick's okay, there we go. Chiming. He's describing a field. It's a scalar field because just one number at each point. Okay, so we're assigning value. Uh, it had several numbers at if it had several numbers at each point, it would be a tensor field because the tensor is basically the map. Okay, I believe that's correct. All right. Welcome, Samaj. Blast from the past. My creative ape brother from another mother. Good to see you, my friend. And again, the dueling thing is just kind of a meme. It's more of like, listen, you say the most out there crazy. I view it as asymptotes. What's the asymptote? You sit around, you do absolutely nothing, complete apathy. Or you take it to the extreme. Everything is so outrageous. Thereby, we can't stand having folks of that disagree with us there, so we must destroy evil. I've heard a lot of culture warriors say that. I don't see the term destroy as much. I occasionally chime in with, well, if you need to destroy these people, then it's legalize dueling. I mean, you literally have the ability to do it. It would be a legal method. We create work for the attorneys, the underwriters, the bookies, and everything. And then I run into the conundrum of, oh my God, this might work. But I digress. I digress. Let's uh let's get back to legally. That's why I say it. Hey, I don't say I'm doing. I'm like legalize it. You also cover your butt for inciting violence. Uh, I think no, you don't incite it. You just give consenting adults the ability to engage in mortal combat under the doctrine of bodily autonomy. It's your body, your choice. If you want to prove the ultimate virtue signal about potentially eating a legal knuckle sandwich, uh, then I probably believe what you're saying. But doing some good math. Okay, so let's get back to Professor Feynman. We're talking about some fields here.
And the number's changes rather, when you go from place to place. If an object is placed at one of these points, at somewhere in space, the force on it is in the direction in which that number, I'll call it the name it's given, called a potential, is in a direction in which that potential changes as quick as it can. And the force is proportional to how fast it changes as you move. That's one statement. That's not enough yet, because I have to tell you now how to determine how the potential varies. I could say the potential varies as 1 over the distance from each object. But that's back to the action at a distance.
Okay, so okay, we're going to the field thing. So the general concept, to my knowledge, is you've got some field. There's numbers associated with all points. Okay, and you got a thing within that field, whatever that thing might be. And if we're going to traverse the field, it will affect the field in different ways. It's kind of like a whole bunch of dots, or okay, I don't know, just want to use a trampoline example. It's like, oh, you put the bowling ball there, and then if you had arrows, it would point in different directions. I mean, that's something about that. And again, conceptually, it does help me. I tend to think. maybe we should get away from those analogies because they're not really. There might be something deeper there that we're missing by glazing it over with just trampolines, so to speak. So, uh, the gradient of the field. Ah, okay. Because a lot of times I just think of it, I'm like, all right, I fill up my tub with some water. Pop, I pop the drain. Stuff starts circling. It's like, okay, well, this water seems to have a gradient there, and then it eventually is going to go down. And if you put some food coloring in there, you would see it seeping, and then you would see it to start to spin around, spin around, spin around. And it would be changing there. It would kind of like be deforming as you were traversing along it there, or at least you would have. I think Rick said it the best way: the gradient is the slope. Cool. Let's continue, Professor Feynman. Let's get to the point.
Idea. However, the force is at a distance, but you can state the law in another way. It says the following. You don't have to know what's going on anywhere outside of a little ball. If you want to know what the potential is here, you tell me what it is on the surface of any ball, no matter how small. You don't have to look outside. You just tell me what is in the neighborhood and how much mass there is in the ball. The rule is this, that the potential at the center is equal to the average of the potential on the little ball surface minus this constant that's over there in the other equation, divided by twice the radius of the ball. Let's suppose the radius of the ball is called A, and then multiplied by the mass that's inside the ball, if the ball is small enough. Now,
I realized I was muted. It started yelling at me. It's okay. So, hold on. Let's let him
you
finish.
see that this law is different than the other one because it only tells what happens at one point in terms of what happens very close by.
Okay. So what I'm saying here is something about the surface of a ball. Okay. That looks like that looks like a big G. That looks like the Newtonian gravitational constant. It's A is just your radius, your length there, and everything. So if you have two of that, then you multiply it there by a mass. It's well, if you've got a Brooklyn accent. Uh, Rick is commenting that it looks like he made that up, and it's he got the wrong answer. 2 pi is about a circle. I agree with that. All right, let's God's has negative 4 pi GM. Okay, to be fair, I'm not even looking at the other equation there, so I have to I have to be fair. Definitely taking some stuff out of context here. So just let's just see what happens. Let's play. So uh ball of an area. Okay, so let's do make 16 pi like area. So a minimum of area. Actually, let's do this. Let's just do big G minus 2 Planck length. The ability of working within one. Okay. So what he had G2A and mass. Mass will cancel out. Like mass. Let's throw brackets on so it just doesn't get confused. Okay. Looks like yeah, so that's close to c squared if we didn't have that 2 in there, right? Okay, yeah, that's c squared. Okay, and then it's giving us length and time. Oh, that's not going to be the right dimensions. That is, oh, the potential on the ball, the average potential on the ball. Okay, so if you were to put it in something like that, um, okay, I don't know. Help, friends in chat. All right. Okay, so hold on. God's law has divergence. Okay, so negative 4 pi. So basically, negative 4 pi GM. Oh, okay. Let's try this. Uh, Negative 4 pi G. Let's try blank mass. All right. Okay, so our divergence is. It's pi. Okay, so I got a circle. Oh. Okay, because if we take the 4 pi off, we'll get uh gonna be Planck length cubed over Planck time squared. Oh no, you meant. Yeah, all right. So length to the third times the negative two. Okay, and then that 4 pi is changing. Ah, okay. So we're saying by the fundamental theorem of calculus, if you go ahead and attack calculus, we're just invoking the fundamental theorem of calculus. Yeah, that's a tough one. That's a tough one to overcome. If you believe calculus is correct, then yeah. I don't know. Is that considered a quote unquote poison pill? I don't know. Hey, welcome, Jedi. Good to see you, my friend. Good to see you, my friend. Yeah, no, it's you have to let me know when you do some more Godzilla talks. I love talking about that type of stuff. Uh okay, okay. Vector calculus. The arrows and stuff like that. No, oh, I'm very easily confused. Okay, yes, yes. Welcome, everyone. So let's. I mean, that was a side little math tangent. So, okay, I only just confused myself further. So let's get back to Professor Feynman. Maybe just listen another time or so. So the general concept is, at least for me, I'll hear stuff. I'll categorize it in different ways in my head. All right, something surface area telling what's going on the inside. That's what I take away from the whole ADS-CFP correspondence, that somehow using 5 dimensions, we can we know what's going on the surface. We can tell exactly what's going on within the interior without knowing the volume, even though if you calculate the surface area, you technically know what the volume is, and long story short, something holographic principle. If we can tell what's going on the outside, we can tell what's going on the inside. Seems like a very weird thing. And then I come across Professor Feynman's lectures on the character of physical law from 1964, and I'm like, it sounds like it's talking about what's going on the surface and being able to tell what will be going on in a theoretical point on the inside. I'm like, that something surface telling what's going on the inside. That's why I'm like, is is it actually new? No, no, I'm sure there's plenty of math and string theory stuff and all that jazz going into it. I mean, I haven't read the paper, so who am I to criticize it? I'm just saying that I'm thinking the concepts, and a whole bunch of smart people are saying this is very amazing, this is very good, great work, cool. And I go back and listen to a Feynman lecture from like 60 something years ago, and it's like, is is he talking about the same thing? At least the general ballpark of concepts seems to be the same. Uh, yeah, Rick is commenting the bathtub analogy. Okay, okay, yeah, being able to tell the divergence and the stuff that's going on. Okay, cool. Uh, all right, all right. Yeah, no, Godzilla movie in a month. Okay, let me know. Again, personal gluttonous, one of my favorites, Godzilla Final Wars. Some folks weren't big fans. Some folks really loved it. I just loved it because Godzilla just went along and like raffle stomped all the monsters, like how you actually kind of wanted to see him destroy all the monsters, but that wasn't quite the case. They just all battled King Ghidorah because, well, plot, bit story. I don't know. Let's see, where are we? That sounds like maybe a container problem issue there. All right, turn the faucet on. You know, or flux is negative. Okay, so it's negative, and then the drain is positive. Yeah, my mind thinks about it in a different way. I just view the source is putting stuff out into the system, and the sink is drawing in. I realize that maybe there isn't a difference there, but I'm sure there probably is an important difference that I'm not seeing. It's just how I conceptualize it. It's source stuff comes out, sink stuff goes in. So I usually view it as negative, although that really does depend upon your perspective, though. So that's fair. Oh no! Don't do it for me. Just do whatever you want. If I happen to be available and it's something interesting, then sure I can give input. Uh, okay, so sources. Okay, sources more stuff in the volume, and the sink takes away stuff from the volume. Okay, cool. Let's go back. Okay, I'll listen to it again 3 times for maximum retention, or at least that's what I learned from Professor Umbridge from Harry Potter. Oh, I'm sure this is nothing to do where they quote unquote Feynman Bros or whatever come from. Just go out there with a pizza chuck or no. I'm sorry. I'm sorry. I'm being unfair. Continue, Professor.
The action at a distance idea. However, the force is at a distance, but you can state the law in another way. It says the following. You don't have to know what's going on anywhere outside of a little ball. If you want to know what the potential is here, you tell me what it is on the surface of any ball, no matter how small. You don't have to look outside. You just tell me what is in the neighborhood and how much mass there is in the ball. The rule is this, that the potential at the center is equal to the average of the potential on the little ball surface minus this constant that's over there in the other equation, divided by twice the radius of the ball. Let's suppose the radius of the ball is called A, and then multiplied by the mass that's inside the ball, if the ball is small enough. Now you see that this law is different than the other one because it only tells what happens at and multiplied by the mass that's inside the ball. If the
Okay. I just noticed something. He says the mass that is inside the ball. Okay. Hypothetically, and again, I'm extracting this to all different areas where I shouldn't. If one were to attempt to do this with a black hole, when you say in the ball, are you saying that within the surface? Hypothetically, I'm just entertaining the crazy idea that there might not necessarily be anything inside a black hole. Maybe literally all the math is at the surface, because when you do the calculation that I don't know, again, just crazy out there idea. Just maybe that's where the difference comes in here. Or is it saying within the ball you're gonna draw something around a thing? You draw a ball around a thing, and then everything within that ball, so to speak, is there. Because then, I mean, even if all the mass in a black hole was on the surface, then you could at least account for it. So maybe this would apply. I'm sorry, that's why I went back. I'm just rampantly conjecturing over here. That's why we have our little forward. Hold on. Let's cover our butts. Where are we? All right, let's get Professor Wolfram to cover our
Although
rears.
this is going to be weird, and it's going to be about a different.
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one Ruliad. I don't think it rules them all. And it might
Yeah,
be
instead
just
it
hyper Rulial Turtles All the Way Down.
yes, it's on the back of an infinite number of hyperrulial turtles. Various people are commenting on the outrage of hacking the universe on a MacBook Air.
I just realized I didn't actually have the turtle meme on that. I actually have a video where it's got like the infinite stack of turtles and then it slides by. Like I made that into a short. God, I need to update so many things. Uh, between between that and poor Fizz getting hit by
I'm
Snowball.
broken. You broke me. Oh no. Oh dear. You guys! You guys!
Oh, that's what happens when you have it snowball X10 or 20 or something like that. Oh, poor wolf girl. Okay. I digress. Yes, poor Fizz. Okay, so okay, hold on, where are we? Let's catch up. Oh, cool. Oh, that would be fun. Cool, Jedi. Source, more stuff from the volume. All right. Divergence equals source minus sink. Ah, source minus sink. So you could have a concept of flow, so to speak. Flux through the 2D closed surface equals divergence in the 3D volume. That is interesting. Looks like ADS-CFT, which is correct but silly. That might be the nicest criticism that I've ever heard of it. Oh, correct but silly. Uh, but A will always be in the hole. Well, there might be a parable somewhere in your chats. Yes, exactly. If listen, if you have a celestial wolf girl, your co-host, I mean, of course you're gonna have a lot of fun. It's oh God, that sounded wrong. I'm not even gonna apologize to Fizz because she already knows. All right. Yeah, I mean, at least if you could have that and use that to help establish some, so to speak, laws, then hey, you could call it the fundamental theorem of calculus because we are, or what is it? Because it is known as infinitesimal calculus. Because originally, I think something, the translation, I believe, is something like small stone or something. Because at one point they were talking about making hypercalculus or infracalculus within the Wolfram sphere, and then I think they settled on infrageometry is one of the things that they're sitting on. Ooh, unlimited calculus. That's got quite the tone for it. I think all the Sith in our audience are going, excellent. Limited calculus. uh, I'm down. Yeah. Yeah, we can do a show on that. When you're in a good place, I know you got to recover, so just get up your strength and we shall make it so. All right, let's go back to the good professor and let's follow up. Let's see this one more time. Okay.
But you can state the law in another way. It says the following. You don't have to know what's going on anywhere outside of a little ball. If you want to know what the potential is here, you tell me what it is on the surface of any ball, no matter how small. You don't have to look outside. You just tell me what is in the neighborhood and how much mass there is in the ball. The rule is this, that the potential at the center is equal to the average of the potential on the little ball surface minus this constant that's over there in the other equation, divided by twice the radius of the ball. Let's suppose the radius of the ball is called A, and then multiplied by the mass that's inside the ball, if the ball is small enough. Now you see that this law is different than the other one because it only tells what happens at one point in terms of what happens very close by. Newton's laws tell what happened at one time in terms of what happens in another instant. It gives from instant to instant how to work it out. But in
Okay. All right. So I'm trying to differentiate what he's saying here. So something about this. He's telling you what's happening or the potential at a distance. Newton's equations apparently are telling you what would happen at a time. Let's go back one more time. I know. Yes, our current human vernacular. Yes, you can use time for so many. Could be a unit. Time could be an expression that we're using to indicate another thing that might be coming up here. It's what is it? Oh, the British comedian. She did a bit on the scientists and time and saying, well, even the smart scientists say that they still have no idea what time is. And it's just, the Rick showed it to me at one point. It's, oh God, I forget her name. She's a British comedian. Very, very silly. Uh, okay. Oh, let's continue.
Law is different than the other one because it only tells what happens at one point in terms of what happens very close by. Newton's laws tell what happened at one time in terms of what happens in another instant. It gives from instant to instant how to work it out. But in space, it leaps from place to place. But this thing is both local in time and also local in space because it depends only on what's in the neighborhood. And there's another way of representing. That's another way. Now, there's a completely different way. See, there's a difference in the philosophy, in the qualitative ideas involved. You don't like action at a distance. You can get away without it.
I just saw everyone playing like, Chad, that's you can get away with it. It's yeah, like you can get away without it. It's I think that's I know as Stephen Wolf brought up before, it's just the sheer fact he spent a good deal of again time with Professor Feynman, and I'm just imagining it's like the ultimate odd couple. You've got like 20-year-old Stephen Wolfram and almost a proper young British chap, 60-year-old Dick Feynman, brass New Yorker and everything. And apparently, Dick Feynman shared a, uh, a secretary with Marie Gell-Mann, basically the person whom invented the term quarks and everything like that. So I think it's not just the dynamic of like, these well-known, established, famous scientists and the poor secretary having to deal with them as they're jabbing at each other and jabbing at each other. And McFlyman would like troll Marie Gell-Mann because he used to speak in a very proper tone and dialect and used to pronounce things the way they were supposed to be in their original tongues and everything. And Stephen Wolfman's like, and Dick Feynman always made fun of this, saying that Marie Gell-Mann would have to literally spit out all this air in order to get the full pronunciations. And I'm just like, okay, you got poor Stephen Wolfram, young, proper British chap between like Marie Gell-Mann, the man that invented quarks, and like Professor Dick Feynman, the progenitor of the Feynman diagrams that we still use today that he wasn't even a fan of, but he just hadn't found any better way to do the computations. And I'm sorry. In my mind, I'm writing it as like a sitcom, but that's my personal view there. Uh, all right, let's continue. That's 5 minutes, has another formulation for us. I only listened to this like a while ago, so I actually don't even remember what comes next.
Now I'll show you one which is philosophically the exact opposite, in which there's no discussion at all about how the thing works its way from place to place, in which the whole thing is an overall statement, as goes as follows. When you have other particles around and you want to know how this one moves from one place to another, you do it as follows. You calculate a certain quantity you invent a possible motion that gets from one given place to some other place that you're interested in.
Oh, I think he's going to the Feynman path integral. This is why he's like, I think he goes into it's like the particle smells out all the potential paths, blah 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 blah, and then I think Veritas even did a video on that, and then Kirkgard Mungle did a video that was kind of a quote unquote takedown of that video, and then Veritasium posted like on their other channel for the first time in a while at an obscure hour and everything. And I don't know. I'm speculating random drama between create. I just I I just know that if you happen to be a well-established channel and you're doing your standard thing, you're doing the bit, the jive that people generally agree upon, and then you have somebody like Kurt who's got a sizable audience, and he puts on a video, and be like, "Yeah, basically this is wrong," and he's like, "What do you even mean by this? The mathematical rigor and everything," and then all of a sudden, what are your response going to say? It's like, "Oh, Mister Dry Mungo, you're obviously wrong." It's like, good man bring out all these terms, and he's like Son Goku, like sparring with all these smart people, so he has all these ideas kind of fresh in his mind at some level or another. Not saying that he knows everything, and again, he doesn't have a PhD in physics. I think Kurt has either undergrad or maybe a master's in physics. Um, so I mean, he seems to be able to talk intelligently with a number of folks on at a pretty high level. So uh, let's see. Yes, yeah. Hey, we have to stay entertained, Jax. I have to inject a monstrous onto the path to real. The rigor is a Mortice in the tenon of physics. Ooh. Uh, oh my God, yeah. No, it's the amount of times where when I actually sit down and I listen to somebody and they'll explain something and I'll sit back and I'll be like, I have never considered that in my life. It happens a fair bit. It happens a good fair bit. Oh, okay, okay. Ah, mortis, rigor mortis in the. Uh, okay, so let's probably actually play rather than just speculate about what he's going to say, because all of a sudden I remember I had this clip for a few more minutes. So continue, Professor.
In a given amount of time, say it wants to go from here to here in an hour, and you want to know by what route it can get from there to there in an hour, by what curve. So what you do is you calculate a quantity guessing the curve. If you try this curve, you calculate a certain number for this quantity. I don't want to just say what the quantity is, but for those who have heard of these terms, this quantity on this route is the average of the difference between the kinetic and potential energy. Now, if you calculate this quantity for this route and for another route, you'll get, of course, different numbers for the answer. But there's one route which gives the least possible number for that. And that's the route that the particle takes. Now we're describing the actual motion, the ellipse.
Path of least, the principle of least action. Yes, aka universe is supposed to be lazy, or at least that's what I hear some folks say. Hey, Poindexter, thank you for doing. We're just going over some of the character of physical law from Professor Feynman's 1964 lecture series right now. Uh, long story short is if you go back through this video at one point, he's talking about if you want to know what effectively I think he's talking about enforces and stuff like that, what would happen at a particular point, you can do a computation. Basically, if you know what's going on within a spherical area there, you should be able to know what's going on there. And I'm just like, again, I hadn't listened to any of this stuff until probably like more recently, within the past year or two. I'd heard about the general concept of like holography and the ADS-CFT correspondence and all that jazz, where it's like, you can tell what's going on the surface, you can tell everything that's going on the inside, and that apparently applies for black holes or something, or whatever those things might be. Um, and again, I think it's like the most cited thingy in physics there, but all I know is back there, I'm just listening to the character law, and then at one point he says, if you have a ball of any size and you can tell what's going on the surface, you could tell what's going on the inside. I'm like, wait. How do you know that? I thought that was something that people didn't really know until like 1997 or whenever Professor Maldacena wrote the holography paper. And then you go back, and it was actually 1978, but I'm like, this is 1964. He's giving these lectures. I'm like, and again, maybe it was just all developed from that and everything, but again, just as a random crazy person on the internet, I'm like, something something. If you know the surface, you can tell what's going on the side. Okay, something something. If you know what's going on the surface, you can tell what's going on the inside. I'm like, it's a rough analogy, and I'm sure it's totally incorrect and everything. But I'm like, the general gist of it is like, it, I I don't know. Like, did we kind of know this general concept about like Rick's talking about like divergence and everything like that via source and sink? So I'm like, and if Professor Feynman's talking about this 61 years ago, I'm like, all right, well, some people knew a bunch of stuff about this. It's like, should, should that whole correspondence be that surprising? Because the surprising thing to me was, it's like, all right, you hear about a thing within the generalized stuff and frames of modern physics and stuff. You're like, that's a very cool thing. People are like, yes, that's really awesome. And you go back to a lecture from like 60 years ago, and you're like, did did he kind of just say like the same thing? Just gets the old noggin and jogging. Feynman diagram. Excuse me. Well, here's the thing. You might enjoy them more than Professor Feynman because at least according to Stephen Wolfram, Stephen Wolfram was like, Dick Feynman was not a fan of it. All this time I spent computing Feynman diagrams because it's he may have invented them, but even he wasn't a fan of them. He's like, Feynman diagrams have to be like the stupidest method of computing these things. He's like, I just haven't found anything better. So I mean, hey, it is what it is. Okay, yeah. The whole we're modeling these things going to infinity in one direction, infinity in the other. So the way I grok this, so to speak, is like the one thing that really stuck with me in high school math was when we had graphing calculators and they taught us about asymptotes. So it's like, all right, you're gonna have this curve. It's gonna go all the way up. It's never gonna quite touch there, and it goes to infinity. And it's gonna go all the way down here. It's gonna never quite touch. It goes to all the infinity. So I'm like, the way I conceptualize pretty much most arguments is like, okay, I listen to what people say. Go all the way to the most extremal thing you could say or do on this side. Take the exact opposite at the most extremal thing, and then see where some realistic point of stuff is. Uh, so if that happens to be, you're going to take it all the way to infinity, and then you're going to go infinity the other way, you're going to cancel it out, and you're assigning the probabilities. The most probabilistic path is likely going to be the path that you take, because, well, unless there's an unknown thing going on there that you can't account for, I mean, that just makes sense. Okay, let Professor Feynman finish his generalized point.
By saying something about the whole curve, we have lost the idea of causality, that the particle's here, it sees the pull, it moves to here, it pulls. Instead of that, in some grand fashion, it smells all the curves around here, all the possibilities, and decides which one to take. This is an example of the wide range of beautiful ways of describing nature, and that when people talk that nature must have causality, well, you could talk about it this way. Nature must be stated in terms of a minimum principle. Well, you can talk about it this way.
See, that's a big part that I really like about this general lecture here. And to be fair, I was only just passively listening to it when I was listening to it like the first time. Um, he's taking the perspective like there are different philosophical ways that one may talk about these different phenomena, depending on the framing of the argument and the model you're laying out. You may attribute different stuff happening by different phenomena. Phenomena. Do, 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 do. I'm sorry, the phenomena meme is stuck in my head. I should probably clip that. But so it's very interesting, and this is this is probably why Stephen Wolfram was different folks were stressing focus on like the philosophy of what I was doing, just because I didn't even really do that much. I just did like the obvious thing. Uh, is because well, math can terrify some folks. And again, it's like I'm not a mathematician stuff. Can I occasionally set up an integral or something like that, some summation? Yeah, if I use the right software and stuff like that, it's like, yeah, I could do that and stuff. But then again, you need the correct data and everything there because you want your best data available. And apparently, within a lot of these large language models, according to was it Brian Rommel, apparently he's a tech guy. He happens to be on Twitter, and he talks about a lot of very timely things. But apparently, the general view of whatever the DeepSeek large language model is they said that they gave it a lot of very good data, so to speak, to have it digest, and that makes me think that I don't know. Are there any repositories with large amounts of really good quality, delicious data for some type of large language model to ingest and put out amazing things? I don't know. We're gonna we're gonna have to see how it plays out. Uh, let's see where are we at. Okay. The QED. See, I've looked at some of those things and just in my head, it makes sense. It's like if you're gonna express all the different potential states again, okay, you're going through there. But then again, the thing that terrifies me about the Feynman diagrams is like, isn't each vertex once you break off? You have like 137 possibilities, or is that just for the photon or something like that? Because I thought that whole quantum electrodynamics is you're using like the fine structure constant or alpha, or you take the amplitude of whatever your thing is, you square it. Basically, if you're using Thad's convention, you would square ja to get the fine structure constant, or the amplitude of the fine structure constant. I think it's the proper terminology that we generally use there. Um, so if you were to take that, my thing is, it's supposed to blow up, at least to my knowledge. And again, I haven't sat around and Feynman diagrams. I haven't studied all that stuff. So who am I to say? But my general knowledge is that to do high computations on a very high level to get precision, you need to go through this. And all I know is if you have multiple vertices out and you have to go up by 137 each time, that's going to blow up pretty quickly. I think why we need supercomputers and why Stephen Wolfram. Oh, simplify. Okay. Fair. I'm sorry. I was ranting on a different thing because okay. I'm just going to stop talking about something that I don't know about. That's probably the best way to do it. Okay. So let's wrap up with Gus Feynman's words here.
Nature must have a local field, Bill. It can do that, and so on. And the question is, which one is right? Now, if these various alternatives are mathematically not exactly equivalent, and if for certain ones there will be different consequences than for others, then that's perfectly all right then, because we have to only to do the experiments to find out which way nature actually chooses to do it. Mostly people come along and they argue philosophically they like this one better than that one, but we have learned from much experience that all intuitions about what nature's going to do philosophically fail. It never works. One just has to work out all the possibilities and just try all the alternatives. Now, in this particular case that I'm talking about here, these theories are exactly equivalent. The mathematical consequences in every one of the different formulations of the three formulations, Newton's laws, the local field method, and this minimum principle, give exactly the same consequences. What do we do then?
Oh, see, that's interesting because at that point they seem to, if it calculates it out, what do you do? Because that's the whole thing. This is where you're kind of getting the general meme of Professor Dick Feynman saying, if your theory doesn't agree with experiment, it's wrong. It's technically supposed to be a well-designed experiment because occasionally experiments can be wrong. Like, I don't know, every once in a while, maybe that Ethernet cable wasn't plugged in all the way and it looked like those neutrinos are going faster than the speed of causality or light in my vacuum or medium. I don't know. There are certain terms where I'm like, I feel like just meaning certain terms because when people say speed of light, it's like they'll say speed of light in the vacuum. It's just like you just say speed of light in the medium. What is the medium? I'm not specifying. I don't know. Is it going through a space? Is it going through air? Is it going through water? Speed of light in the medium. If we say that enough times, I feel like people will be like, oh, and just kind of get the concept, like a very small twist to something that people hear all the time. Just a very slight change can have a very large effect, I claim. Let's finish with a point. What do we do, Professor Feynman, in this instance? What happens when the experiment agrees, but we have different philosophical outtakes? Please,
You will
yes.
read in all the books that we therefore cannot decide scientifically on one or the other. That's true. They're not equivalent. They are equivalent. Scientifically, it is impossible to make a decision. Because there's no experimental way to distinguish if all the consequences are the same. Psychologically, they're very different in two ways. First, philosophically, you like them or don't like them. Training is the only thing you can do to beat that disease. Second, psychologically, they're different because they're completely unequivalent when you go to guess at a new law. As long as a physics is incomplete and we're trying to find out the other laws and to understand the other laws, then the different possible formulations give clues as to what might happen in other circumstances.
Okay. Bingo. Bingo, bongo. I can say that. I think it's best faster fine. I'm like, play the bongos. I think his intro is like, yes, yes. I do more than just play the bongos. I actually do physics. It's you listen to some of his lectures, and I'm just sitting back. I'm just like, is this guy like a physicist or like a stand-up comedian? That's why I asked Stephen Wolf from that at one point. It's because I'm like listening to the crowd laugh. That was my intro to just Professor Feynman thing, not like these lectures, but just Los Alamos, where he's like, the crowd is roaring and laughter and stuff. So I mean, hey, it's got to be engaging. Like Jack's is saying, it's like you gotta have some fun and stuff like that. That's the thing. It's I mean, you got to have fun because it's yeah, if you're not having fun, it's just like, oh God, it's everything is like a chore and everything. So a lot of that is also perspective. And again, I've totally messed that up and had my perspective, if my have my perspective go in different ways that were very negative, and it's like, oh my God, I tweak it a little bit. Oh my God, this is an opportunity. What am I even? Yes, yes. Fully Nexus point out, but even quote unquote vacuums, aka, are filled with quantum fluctuations. The virtual particles popping in and out is it possible they affect photons as well? That's a very good question. I don't know. This is some of the key questions at our time. But to wrap up, what Professor Feynman just stated there, it's like, okay, if you're getting the same answers for certain things, now, as long as we are incomplete, as long as we don't necessarily know what might be the deepest stuff that might be going on, the quote unquote bottom turtles, so to speak, in a method of saying. And again, that's probably not the greatest analogy, but if we could figure out the root, the fundamental, within Wolfram physics terminology, the aims of existence, the atoms of existence, space, or the elementary components of our reality. That's the thing. Depending on which perspective you're using, they will give you different clues. And then as you probe into what might be going on to extend our explanatory power to the next level, so to speak, um, you would see different things. So as we get those clues, as we figure out better what might be going on within our realm of persistence, um, yeah, those should help guide our path. And as we become less wrong, hopefully, we'll actually become a little bit more right. That's that's about what I got for right now. Um, Yeah, so that's for over and out. I need to finish putting up a lawnmower and mow my messy lawn that I have not taken care of in so long. Sorry, it's like 90. There's like a heat advisory. It's like 90 to 100 for like the rest of the month right now. And Yeah, I should do that so my neighbors stop giving me the angry eye. Yeah, I don't know. Questions are very good. Uh, yeah, that is very true. There is the one you talk to and the ones that hear you talk. We talk to all different folks here, and one of the slightly confusing things is remember, nobody would ever get confused about who somebody is talking to within the internet. Doesn't matter if you're on this website, doesn't matter if you're on any of the other websites. I'm sure nobody's ever gotten into a fight with somebody that wasn't even talking about them on the internet. But I digress. So that's all we got for right now. Hey, thank you all for watching. Oh yes, I'm sorry, Bill. We're wrapping up right now. I gotta go mow the lawn, put together my new lawnmower and stuff. So gotta gotta keep people happy. But yeah, we are just talking about it and how Professor Feynman, the links in the doobly doo below. Uh, we have been talking about something quite similar about 61 years ago. And again, it's probably just me, but yeah. Oh, well, that's all we got. So I'm curious your thoughts. Feel free to comment down below if you like. But other than that, take care, everyone. It's a wacky and wild world out there, but it's open for a better tomorrow. Peace out, everybody.